Hello, today I want to introduce TEM sample preparation. My colleague Witin gave a talk about this recently, and I reformed his PPT and I prepared my lecture for posting this video. I personally believe the sample preparation step is one of the most important and demanding part of TEM experiment. The quality of your data will directly proportional to the quality of your specimen, and even the efficiency and reliability of your produced data strongly depends on the quality of the sample as well. So it is always better to know as many as possible solutions or ways of sample preparation when you want to do TEM. So you can also call this recipe for the TEM sample preparation, and today I'm going to introduce to you. First of all, there are several constraints of TEM sample itself. The TEM is transmission electron microscope. So you want to have the sample which are electron transparent. So one principle to make the sample electron transparent is making it as thin as possible. So generally speaking, the thin specimens are better in TEM measurement. The specimens thinner than 100 nanometer are required for general TEM measurement. Of course, it is a function of the mean free path of electron in the sample. So for high resolution TEM or electron spectroscopy measurement, the sample thickness of less than 50 nanometer or even less than 10 nanometer is required. But these restrictions get reduced as the beam voltage increase, but the increase of the beam voltage can cause a damage in the specimens and may create some artifacts during the measurement. Another important point is that the sample should not be affected too much by the sample preparation step. So a stable sample is actually better, but here this table show some possible artifacts are produced by the sample preparation step. As I told you, the thickness is the thing strongly affect your data. If you have an inhomogeneous thickness all over the sample, you will have the limited area can be measured in TEM, and the error signal from the thickness variance will significantly impact your observation. So you may also think about, for example, the surface oxidation as an artifact, like a preferential, like the elementary thinning may make very difficult to comprehend your data. You also induce undesired defect during a preparation of the, for example, in FIB, like a focus ion beam thinning process, the gallium implantation and or the redeposition can be artifact. Many kinds of possible artifacts can be with you in the real experiment, and you should be aware during the sample preparation, and also very importantly, when you are doing data analysis, you should be always keep in mind that there are some possible artifacts. So there can be many kinds of original materials for your TEM observation: the powder, bulk, thin film, and biological materials, so on. So our approach for the TEM preparation would differ and depends on the properties and geometry of the original materials. So in terms of sampling, you may have self-supporting sample or the sample resting on the support grid. For example, if you are interested in powders, you most likely use a supporting grid. The grid is made of copper frame, and the film to physically support the powder-like sample. So you can finally stick your powder on the grid. And also there is another possibility. So alternatively, you can make up the bulk-like sample from powder with the pressing into a pellet. So then you can make it self-supporting powder. So you also have bulk materials that you need to make them small enough firstly, then you need to thin down. And there are many ways to deal with the sample. Like also there are some thin film sample and biological materials, and those ways that I will introduce in detail shortly. So firstly, let us take a look at how to prepare the powder samples in detail. So you know, powder are of strong interest in the industry nowadays since they have a larger surface and possibly easy for application in industry. So the easiest way is to put the powder on the grid and observe. Which usually mix the powder in aqueous solvent, which are normally ethanol, and to distribute the powder sample homogeneously. So we call this mixture as a suspension, and there is the heterogeneous mixture in which the solid particles are not dissolved, should not dissolve because we need to observe in the TEM. But they left floating around freely in the medium, and we just immerse the sample grid in the suspension and dry it. It is little simple, but you should think about the chemical reaction during mixing, and if your sample is not enough in density in your suspension, it will be difficult to find your sample when you are doing TEM. So alternatively, you can mix up the powder with epoxy. Just stir and mount, and we get disc-like sample, and you can further thin down after making disc. You see this picture that this gray area is epoxy, and these debris are samples of interest. And you can also embed the particle in the metallic matrix. This picture shows the procedure. This shows a setup for sample preparation, including ceramic powder. And under the research, actually here is ceramic powders are of interest, and fine copper powder, and the aluminum oxide the mortar, and the pestle for powder mixing, and steel die for pallet pressing. And this is a ceramic powder mixed with copper powder in a certain volume ratio and put into the steel die for pressing. And the mixture on aluminum stove before pressing, and the mixture pressed into the pallet under the certain pressure. The mixture pressed onto the pallet on the aluminum tube, and glue on the part of the pallet on the copper slot grid, and then mounting the sample on the precision ion polishing system, and apply a low voltage milling like a 3 electron volt or less than that, with the low angle of the incident to reduce the damage of the surface. And you can get the sample like this. Then you will observe supporting copper matrix, and those particles are the area of interest. And you can also go to higher resolution. But in this research, I guess the sample is not very thin enough, for sure, but we still can observe the lattices. In case of the bulk material, the general procedure for the way of the sample preparation, we need 3 different individual setups: the cutting disc, and pre-thinning, and final thinning. Obviously, we will have a big sample, then you need to make it small enough to be applicable for the further thinning session. So we use several devices for that. This one is a mechanical punch for stamping disc from the thin sheet sample, and this is abrasive slurry disc cutter, and this is ultrasonic cutter, and this is spark erosion cutter. The erosion takes place there under the solvent, and behind a safety shield. These are just all about making samples small enough for further steps. In this step, you need to think about the possible mechanical damages. If the material is reasonably ductile, then the mechanical damage is not so crucial. But during the punching, the shock can induce the shear transformation in some material, especially for for the brittle materials. In this case, spark ultrasonic drilling and using a grinding drill will be possibly the better options than the punching. But keep in mind that such like for example, the spark illusion can only be used for conducting samples. So there are also some limitations and constraints that we need to think about. And you can also induce high temperature during the cutting, for example, like a drilling also in the spark illusion. So the temperature induced artifacts will be also should be in consideration. After making disc, then we go for pre-thinning process. The aim of this process is just to thin down the center of the disc with the higher the efficiency while minimizing damage to the surface of the sample. So you can also thin down your sample manually, obviously, but it is not so easy to get the flat sample and good sample. But if you do this, it is recommended to change the sample angle, sliding angle, to reduce preferential thinning. So it is quite good way, just number 8 like track thinning, because you always thin the sample down with always changing the angles. As written here, the sandpaper with the particle size should be step by step reduced, like P1000 to 2000, something like this. The thinner sample is the larger the type of sandpaper should be used. After you are done the thinning with the certain number type of the sandpaper, you should wash your sample properly. Otherwise, the remaining ceramic particle from the paper will be existing and scratch your sample in the next final thinning process. So yeah, we can also thin down automatically using the dimple grinder. This is, in general, we refer to this stage just dimpling, no matter how the thinning is achieved. Most commercial mechanical dimpler use a small radius tool in the picture here, and here we grind and polish the disc, a fixed radius and curvature in the center. So you can control the load, of course, and you can precisely determine the target, the thickness of the sample. The thinning disc using dimple grinder has several advantages, like for example, large transparent window you can get, depends on your interest. If you need a larger scale information of the sample, the dimpling is a sort of good try. And the prepared sample is mostly self-supporting in this case. And you can also control accurately the thickness at the end, I mean. So if you have a decent machine, you can also precisely control the position of the thinning, so you can specify your area of interest. Okay, this is electropolishing. The electropolishing can be only used for electrically conducting samples such as metals and alloys. A certain voltage applied at which the current due to anodic dissolution of the specimen create a polishing surface. The classical jet polish is shown in this figure. The sample is placed in between the copper rings and painted with so-called the lacomite. And the sample is located in the sample holder. Normally a twin jet apertures are used to pump the jet of the electrolyte onto the both sides of the dimpled disc, and due to the electrochemistry, the sample be etched and polished. The biggest advantage of this electropolishing is that it can produce the thin foil without mechanical damage. But problem is that it can change the surface chemistry of the specimen. To reduce the chemical artifact, you need to apply the certain voltage range, in appropriate range of so that the etching or pitting does not occur. The ion milling involved bombarding. This is a ion milling, so this is actually descent technique, and the ion milling involves the bombarding your delicate thin TEM sample with energetic ions or neutral atoms until it is thin enough to be studied in the TEM. The schematic diagram and the commercial model are shown here. The variables which you control include the voltage temperature of the specimen. Often aligned the ion beam at an angle like 15 and 20 degree to the surface. We need to care the preferential thinning and minimize ion implantation. So it is important to play with the angle of incidence ion. The thinning rate is strongly, but the thinning rate strongly depends on the angle. So if you use a lower beam energy or lower G ion, you can reduce the beam damage, but in both cases, the milling time will increase. The ion milling is the most versatile thinning process nowadays, but thinning mechanism of ion milling is very, very complicated and complex, and there is a big material dependency during the thinning process. So materials thin at a different rate, so it is always recommended keep a record of what kind of conditions you are using, like a beam. You should write down the beam current and angle of incidence and rotation rate and acceleration, voltage, so on. So we need to be always aware of possible artifacts like ion implantation and the beam damage. So it is usually recommended using the gradually decreasing value of voltage to final thinning process to reduce the surface damage. And the microtome has long been used for sectioning biological materials, and biologists can reconstruct a 3D picture of the biospecimen. In recent research, the brain has been investigated with comprehensive neutral circuit mapping. So in this work, the biological sample was prepared by a microtome. The ultramicrotome operates by moving the several tens of nanometer the specimens past the knife blade. Then this blade can be a glass. Actually, glass is cheap but it should be used for soft materials. But there is some blade with the diamond which can be used for harder, the origin materials. These methods are among the oldest TEM preparation technique, so-called the replication of and it has been used to study the fracture surface or the surface topography in general. The procedures are to the procedure is to evaporate a carbon film on the surface of interest, then etch away the underlying surface and on etch it, and the carbon film float up after you etch the plastic. And you can also spray the acetone on the plastic there, and your surface is to be replicated before pressing a plastic onto the surface, which is often in contact with an acetone. The plastic is removed from the surface when it is hardened, and copper, chrome or platinum film is evaporated onto the replicated plastic surface. But alternatively, we can directly carbon replica of a metal surface. Here we use a technique developed for advanced engineering application. Here is we call lithography. It's used in the microelectronics industry to define a fine electronic lines. of which the width can be down to several nanometer. So we can draw a line on the layered material using standard lithographic techniques. The material on either side of the line can be removed by etching, and material either side of the lines can be removed to give a plateau which is thin in the one direction. When the remove most of the remaining, we can also remove the remaining like a part like here, and we can directly observe the sample by TEM of the thin film. For the last thing, I prepared the FIB. The focus ion beam instrument is really versatile and becoming much more readily available nowadays. I'm gonna separately post a video for introduction of FIB sample preparation, but in this video I just point out several general things. When preparing TEM specimen with FIB, we can think of the built-in ion milling system in an SEM, like the scanning electron microscope. The single ion gun produces a well-defined controlled beam of gallium or the argon ions. Then they actually usually used as bombarding ions. So this bombardment, you actually the focused ion beam actually thin or etch to make sample, desired sample. Then in this case, we firstly deposit the PT layer on the top of the region of the interest to protect the region. Then we mirror out both sides of the sample to get the TEM lamella. Before we take out the sample, in order to make it facilitate, we need to make the sample be halfly free. So we call here is a J cut or someone say like a D cut. Then we put the Omni probe, which is precisely controllable needles in the system, and to take the sample out and put on the grid and glue. Then we thin down the sample in both sides with the focused ion beam again. In practice, you need to think about many details, so that is gonna be the reason why the preparing another lecture for that. So these are all about today actually, but I very briefly go for the just to show you some entire picture of sample preparation. But in the future, as I told you, I will individually select one topic and go a little bit deeper. And for the first thing, maybe I will prepare the focused ion beam sample preparation, which is nowadays very popular for many kinds of materials. And I hope this general talk will helpful for you, and I'll come back soon. Thank you for listening.